Chem Mastery. Your study buddies.
Hi everyone, my name is Hannah, and this week we are going to look into a new chapter, which is about the rate of reaction, and I'll be the one explaining it to you all. In this chapter, there are a few things we will discuss. We'll discuss what is the rate of reaction, the changes that occur, such as what are the changes that are observable, the type of rate of reactions, and the factors affecting the rate of reactions. Before we start, here are some quotes for you to remember from Albert Einstein. Anyone who has never made a mistake has never tried anything new. And we should learn from our mistakes by first understanding each mistake. And if you can't explain it to a 6-year-old, you don't understand it yourself. Alright, to start off, what is the rate of reaction? So, the rate of reaction is the changes in the quantity of the reactant per unit time, or the changes in the quantity of product per unit time. This basically means that the rate of reaction is how fast our reaction occurs. Some reactions can be slow and some occurs really fast. And that is what we mean by the rate of reaction. The changes on quantity of reactant or product here could be in the changes in mass, concentration, or volume. To find the rate of reaction, we can divide the changes on quantity of reactant or product by the changes in time. There are several units for this rate of reactions, depending on the parameter we use on the dx here. If we use mass over time, it will be gram per second. If we use the concentration over time, the unit will be molar per second. And if we use volume, it will be centimeter cube per second. Note that the unit of time can also vary if a reaction is fast. If a reaction is fast, then we will usually use seconds. But if a reaction is slow, we will use minutes. So, if you ever thought about why your food goes bad much faster when you leave it outside than when you put it in the fridge, or why does your food cooks much faster when you use high heat instead of low heat? Well, all of these are related to the rate of reaction. Alright, now let's look into the changes that occur during reactions. They have to be observable and measurable. So the formation of precipitate here is a reaction that produces insoluble salt. For example, the silver nitrate reacted with potassium iodide, it will produce silver iodide and potassium nitrate. The silver iodide produced is in the form of precipitate, which you can see in this picture here. There are also reactions that causes the reactant to decrease in mass and produces gas, such as this zinc reacted with hydrogen chloride to produce zinc chloride and hydrogen gas. If we were to measure the mass of the zinc after the reaction, we will observe that the zinc have decreased in mass, and since the hydrogen is produced, the hydrogen gas will increase in volume. These changes are important for us to observe, see how fast or how slow a reaction occurs. It is for us to know that a reaction is happening so we can calculate and measure its rate of reaction. Now let's look into the types of the rate of reaction. There are two types. The first is the average rate of reaction, and the second is the instantaneous rate of reaction. The average rate of reaction is the average value for the rate of reaction that occurs in a particular time interval. That means we are looking into the rate of reaction within a certain time interval. And how do we calculate it? So if we have a graph like this, which is the volume of gas in centimeter cube versus time in seconds, we can simply take 2 points from the graph and find out their respective volume and time. So just like in here, we have 2 points and we write it down as T1 and T2 for the time and V1 and V2 for the volume. So what we do now is just V2 minus V1, which is the change in the volume, divided by T2 minus T1, which is the change in time. And by that, we can get the average rate of reaction. As for the instantaneous rate of reaction, instantaneous rate of reaction is the rate of reaction at a particular point of time. So we're not looking at the change of the volume over a certain time interval, but we're looking for the rate in a specific point of time. So for example here, we want to find the rate in time t. Now how do we do that? We make a tangent at that point, like this. And we calculate its slope or gradient. And so we can use the gradient formula where we take the points of the slope. So we take this V2 and V1 and T2 with T1. So do not confuse it with the average rate of reaction because we use the gradient for the points in instantaneous rate of reaction. We have these two types of rate because sometimes we want to measure its average rate in a reaction. We want to know the rate within a specific time interval, while sometimes we might want to find out the rate at an exact point of time. So it depends on what we want to measure. If we want to know the rate at time t, we find its slope, and if we want to know the rate within a certain time interval, we use the average rate of reaction formula. So I hope so far you can understand what is the rate of reaction, the changes that occur, and also the types of the rate of reaction. As now we will be looking into the factors affecting the rate of reaction. We have several factors here. The first is the size. The size means the total surface area of the reactant, like is it in powder form, in granules, or in chunks? Whatever form of reactant we use, it will affect the rate of reaction. Next, we have the concentration, which is the concentration of the reactants reacting in a reaction. If we have different concentrations of the same solutions, let's say 0.1 molar and 0.2 molar as a reactant in a reaction, we will observe that their rate will differ from each other, assuming the other variables are the same. And another factor is catalysts, where catalysts can lower the activation energy and speed up their rate of reaction. We will talk about this further as we go along. And so our last factor is the temperature. Remember when I talked about why using high heat in cooking can make our food cook faster than when we use low heat? Surely this has something to do with our factor here, the temperature. So we'll now take a closer look at each of these factors that affects the rate of reaction. Okay, so first of all, size. So why does the size matters in the rate of reaction? Well, this has something to do with the surface area. If we look at this first picture here, the molecules are all very close to one another. They're basically sticking to each other. So the surface is only limited to the top, bottom, and the left and right sides here, which are exposed. But if we were to cut them up, we were to break them, we will get this scattered molecules here where their surface area will increase and they will be able to collide with each other more often. So the frequency of the collision between the reactant particles increase, which will also increase the frequency of the effective collisions of the reactant particles, hence increasing the rate of reaction. Notice that there's the frequency of collision between reactant particles and also the frequency of effective collisions. So what is the difference? A collision can happen even without the reactant particles being in the correct orientation. So they might just collide with each other, but they may not form a bond as they have the wrong orientation. On the other hand, effective collisions is when one reactant molecule and another reactant molecule collide with each other in the correct orientation and forms a bond. So for example, we have two reactants A and B. Since we want them to react with each other, the effective collisions will happen when the particle from A collides in the correct orientation with particle B to form a bond producing the product C. The higher the frequency of effective collisions, the higher the rate of reaction. So that means that the rate of reaction depends on this frequency of effective collisions. Okay, so an easier way to understand how the size affects the rate is by looking at this picture here of coffee beans and coffee powder. Let's say we put these coffee beans into hot water in a cup and another cup we put this coffee powder with hot water and we stir both cups. Which one do you think will dissolve faster? Of course, it will be the coffee powder with the hot water, right? This is because in coffee powder, there's more contact surface area, so it increases the collision of these particles, hence it will increase the reaction rate. Coffee beans, on the other hand, have smaller surface area, so they will need more time to dissolve as they have a lower rate of reaction. So the important thing here is the higher the contact surface area, the higher rate of reaction. So reactant in the powder form like this will react faster than the coffee beans, which have lower surface area. It is also why when we want to make coffee, the coffee beans will usually need to be grinded first. Our second factor here is the concentration. Why is there written liquid there? Because there's another concentration which is for gas, but in this slide we will focus on concentration in liquid. So how does this concentration affect the rate of reaction? As the concentration of the reactants increase, it will increase the number of reacting particles per unit volume, because we know that the unit of concentration is mole per liter. Increasing the concentration means increasing the number of moles per liter. And if we have more moles, we will have more of these particles. If the number of the particles increases, the frequency of collision between the reactant particles increases, just like in this picture here on the right. They have less space to go around, and they'll end up colliding with each other more often, and so increases the frequency of effective collisions. Thus, it will increase the overall rate of reaction, which is why when we have a 0.1 molar and a 0.2 molar of the same solution as a reactant in a reaction, the 0.2 molar will have a faster rate, assuming that the other variables are the same. The concentration in gas is similar to the one in the liquid, but in here we use pressure. Changing the pressure in gas is the same as changing its concentration. So when the pressure increases, the concentration also increases, which means the collision between the reactant particles will happen more frequently, and more collisions means more effective collisions, and hence increasing the rate of reaction. Note that when pressure increases, the volume decreases just like in this formula here. P1 V1 over T1 is equal to P2 V2 over T2. So the pressure and volume are inversely proportional. If pressure increases, the volume will decrease, and vice versa. If the pressure decreases, the volume will increase. Just like this picture here on the left bottle, it has lower pressure, so that means it has a higher volume, and we can see the particles have more space to move around, so it has lower frequency of colliding with each other. But on our right bottle here, it has a higher pressure, and so the volume is smaller. This makes the particles more restricted on where they can move, and so they will collide with each other more often, which increases the frequency of effective collisions. Which is why the bottle on the right here will have a higher rate of reaction than the left one, which has a lower pressure and thus a lower rate of reaction. Our next factor here is the temperature. When the temperature increases, the kinetic energy of the reactant particles also increases. This means that in higher temperature, the particles are more energetic, so they will collide with each other more often than in the low temperature where they won't be as energetic. You can see in this picture here, in the low temperature, only some of the particles are colliding with each other. But in the right-hand side, in high temperature, there are more molecules that are colliding with each other. And we know that from the other factors we've discussed, if we increase the frequency of collisions of the reactant particles, it will also increase the effective collisions between these particles. Another reason why the increase in temperature can increase the rate of reaction is because when the particles have more energy, they can overcome the activation energy that is needed for the reaction to occur. We will talk more about this activation energy in the next few slides. So, as to answer why cooking at higher temperature will cook our food much faster than when we use low heat, is because of the kinetic energy the particles in our food will gain from the high temperature, since they become more energetic, and as they collide more often, the rate of the reaction that is happening is occurring at a much faster rate, so we won't have to wait for a long time to be able to enjoy our food. Okay, so I mentioned before that when more particles have more energy, they can overcome the activation energy that is needed for a reaction to occur. So, what exactly is this activation energy? Activation energy, denoted as EA, is like an energy barrier that needs to be overcome by the reactant particles before a reaction can take place. So, it means that this activation energy is the minimum energy needed for a reaction to take place. This energy is used to break the bonds in the reacting particles to form the new bonds in the resulting products. All reactions will need this activation energy, and it has to be overcome by the reactant particles in order to form the product we want. It is like this picture here. The hill that needs to be overcome by this blue particle here in order to go down, which is the product. So an example of this activation energy is like when we are camping outside and we want to light up a fire using some tree branches. We will need a lighter or a match that is like the activation energy to produce the fire. So it's like something to ignite, to give the spark, to produce the fire. Okay, last but not least, we have our last factor here, which is the catalyst. Now, what does this catalyst do? Well, this catalyst provides an alternative pathway in the reaction by lowering the activation energy. As I said before, the activation energy is something that needs to be overcome, and this catalyst will help us to reduce the amount of the activation energy needed for that reaction. So if we look at this graph here, we can see the green line is without the catalyst. It's a big hill that needs to be overcome by the reacting particles. But if we use the catalyst, the pathway will be this purple line here, which is like a smaller hill. So it is easier for the reactant particles to form the product. When we use this catalyst, more reactant particles can achieve the activation energy. And the frequency of effective collisions between the particles will also increase, and thus also increase the overall reaction rate. Using a catalyst is very helpful, especially when we're dealing with slow reactions, as it can help to fasten the rate. I have a picture here which shows mountains and two pathways, A and B. Now, which pathway should we take if we want to reach the destination faster? Well, of course, we will take pathway A, right? A tunnel that directly leads to our destination, rather than path B, where we will have to go around the mountain and go from one mountain to another to reach our destination. The mountain here is like the activation energy, and the tunnel is like the catalyst. So if we use pathway B, we will have to go up the mountain and go from one mountain to another, which will take much more time to reach our destination. But if we use the catalyst here, which is the tunnel, it can help us to reach our destination much faster. Okay, so I hope by now you understand what is the rate of reaction, the changes that occur during the reaction, the types of the rate of reaction, and the 4 factors and how they affect the rate of reaction, such as the size, the temperature, concentration, and catalyst. Another quote for you here: education is the most powerful weapon which you can use to change the world. So some special reminders. We have a factor, elaborate, the frequency of collision, the frequency of effective collision, and the increase in rate. For each of the factors we should be able to understand how it affects the rate of reaction, how does it increase the frequency of collision, thus increasing the frequency of effective collision, and how it increases the rate of reaction. Keep in mind that the determining factor of the rate of reaction is in the frequency of effective collisions. We have seen that all the factors had this increase of effective collisions, because more effective collisions, more product is formed, and hence increase the rate of reaction. Here are some tutorial questions for you to answer. There are 3 questions. The first question is: define the rate of reaction, the frequency of collision, and the frequency of effective collision. I hope you can answer this as we have discussed it before. The second question is this: 2 experiment was carried out using magnesium ribbon of same length to react with the acids as shown below. 150 ml of 1 molar hydrochloric acid, 100 ml of 1 molar sulfuric acid, and so we have to determine which experiment has a higher rate of reaction, and include a calculation and sketch graph in your answer. And our last question here, we have 2 graphs. An excess amount of granulated zinc is added to 100 ml of 0.5 molar hydrochloric acid. The gas liberated is collected at intervals of 30 seconds. A graph of volume against time is shown by the curve X at STB. Now you have to state 3 different ways to obtain the curve Y for each graph. Then sketch a graph of volume against time if the acid is replaced with sulfuric acid with the same volume and molarity, and you need to show the volume of gas. Calculate the value of alpha and beta. Explain the effect rate of reaction if the experiment is carried out using 100 ml of 0.25 molar sulfuric acid. And why does the reaction stop at beta volume of gas for the graph, or for the second graph? So I hope you can answer the tutorial questions, as the answers will be discussed in our next video. And just like the previous chapters, we also have a quiz for you to participate in. there will be 10 objective questions based on this chapter, and you can get the link here. And once you enter the room, please write down your full name, and you can only access the quiz one time, and it will only be open for 1 week. So please read and follow the rules and regulations, and good luck in answering the quiz, as there are prizes that awaits you. And this is my team that worked on preparing this chapter. So I hope you enjoyed it, and that it is of use to you all. Thank you very much. Thank you.